And before we get going today, just want to issue the reminder, bad news, Thursday, no class. Okay, I'll be having the surgery, and I'm pretty sure, even if the doctor said I could come, my wife will say I can't. Okay, so,
I want you to come.
yeah,
Rest.
right. And I think I will be resting. So,
Happy Father's Day to you.
oh, well, thank you. I don't have any kids, but thank you.
Your father a lot on here, I suppose.
Yeah. And so now, did we talk about, do we want to try to make up the time I'm missing because of the surgery, or just follow it on the YouTube video? Because I can either come a little early or stay a little later, and we can, spread it over several classes and make up the time that way. Or you can watch the YouTube video, and we'll go over that before the end of class today. Which would you rather do?
What's more convenient for you to do?
I'm happy either way. I know if I know some of you can't come any earlier, right? Okay. Is it inconvenient to stay a little later? No? No? You want to do that then, and do it over several days and make up the time that way? And that way you can ask questions. You can't ask questions of a video, but so, okay. So what you want to say, it's an hour-and-a-half class, so we could do 15 minutes extra a day for 6 classes, or we can do a half-hour extra a day for 3 classes.
Half hour.
Half hour for 3 classes. So you want to start today?
I guess so.
Okay, not today. Okay, so next week, Tuesday, Thursday, and the following Tuesday, we'll go until 7 rather than 6:30.
Right.
Is that all right? Okay, we'll do that then. Okay, that's settled, and I hope that'll be okay with Haley.
I text her to test you, never text back.
What's that?
I text her to test her. I don't know if she
Right.
dropped the class or what.
Okay.
She never responded.
Right, and I haven't seen Addison Gray Nelson yet at all. Now, Haley has paid for the course, so I assume she was going to want to stay in it, but that's just an assumption. All right, any questions on anything we've covered so far? Okay, then we're on page 202 for those who do have a text. We just finished talking about what is work, and the simple definition of work. Let me get my pen set up. I've got to pay attention and make sure my cord stays connected here. That work is equal to a force times a displacement. With a caveat. The force is either the component of force in the direction of the displacement, or the displacement in the direction of the force. One or the other, but they have to be collinear. I think I explained before, if I push like this on the chair, I'm pushing this way, the chair is moving that way. The amount of force I exerted the amount of work I'm doing on the chair is the force, whatever that is, times whatever displacement. That's work done. Now, if I push like this, you can't tell, but I'm pushing harder and not making as much progress, because you see, this force isn't making the movement. It's only the component of the force that's in the direction of the motion. And we're going to get to that a little bit later. So it's force in the direction of the motion times the amount of movement. Force times displacement, as long as they are in the same line. Okay. Does that kind of make sense?
Force time.
Force times the, and the book uses, I use D, the book uses S. That means that's what they use for displacement. What's that?
Use the S instead of the D.
They use S rather than D. It means the same thing. It's just what letter you use. Okay, that's sort of a generic letter for displacement, but D is pretty generic too. But most other books use D. S is just displacement. It stands for the same thing. It's just this book uses S. Most other texts use D. It doesn't matter what you call it, Fred, Sue, whatever. It's the same thing. Okay? Now, from that equation for work, that one right there, we can determine the units for work. And I thought we did this last time, didn't we? I think we did. What's the units for force?
The units for force.
Yeah, capital N is Newton. And displacement is measured in? Okay, it's entered is meters. So 1 unit for work is a Newton meter, but it has its own name. Does anyone recall what that was? I think I told you last time. A joule, okay? And that's a capital J because it's named after James Prescott Joule. So the unit for work in the SI system is either Newton meter or joules. Now, in the U.S. customary system, what's your unit for force? Second? When I stand on the scales, what are we reading? Pounds, okay. And in the SI system, what's your unit for displacement? No, that's mass. Displacement. A length. Huh? A length.
Let me look at my notes.
It's a foot.
Foot, yeah.
Okay. I can't raise my leg any further. Okay. All right. So this unit, it doesn't have a special name. It's just, usually we don't say pounds feet, we say foot pounds. Foot pounds. That's the unit for work in the U.S. customary. Okay. Used to be called the British system, but technically the British don't use it anymore. We're about the only people that do. Though, most Brits still use it, okay? But they officially use SI units now. Okay. Now, Newton forces are vector quantities. They have directions as well as magnitude. Displacements are vector quantities. That's why the direction matters there. But work is not a vector quantity. It's a scalar quantity. And the reason for that is, and you don't need to know this, even though these two are both vectors, force is a vector, displacement is a vector, you're doing what they call a dot product, which produces a scalar number. So work has no direction. It's just work, okay? It's just a scalar quantity. All right. I thought we did, I'm looking at the wrong, we did do all that. Okay, I have another mark here. I had forgotten to erase my previous mark. Sorry about this. Because we did the guy lifting the bricks. I remember that now, right? Sorry, that was a review, by the way, okay? So let's look at example 2. That's where we should have begun. A worker pushes a 350-pound cart. Okay, let me clear my screen here so we have a full screen to write on. Okay. My worker is a stick man. Okay, it's not a pretty looking guy like that is. Okay, it's a stick man, and he's pushing a cart. Okay, here's the handle of the cart. Okay, and this cart is 350 pounds. Oh, it's loaded with stuff too, okay? You can see that. It has blocks and bricks and all sorts of things on it. Okay, it's piled up here. And the weight of that, force due to gravity, force of weight, is 350 pounds. Okay? They don't put a bar over the 0, and there is going to be a reason for that in a minute. He pushes this car a distance of 30 feet. Okay, that's your S. Hi, here's Haley. Now, I don't know if you heard the video from the last class, but if you didn't, important announcement. I have cataract surgery on Thursday, so I will not be on campus all day long.
Okay.
So no class on Thursday, okay?
Can I get a copy of the test?
Yes. I made a copy for you in the class last time. I only had 3, but you weren't here, so there it is. Okay, and let's see if there's anything special about it. I corrected the number 7. The way it was written, 17,500 pound pulling force, it wouldn't have pulled a single car. When I did the work backwards from the answer, I found out they left off a 0. Should be 175,000 pound pulling force. So that correction is on there. Okay. Now, so what the others decided before you got here, how to make up for the time I'm going to miss because I'm here on Thursday. We decided, do you have any problem staying 30 minutes later? Not today, but in the future.
No.
Okay, so what we'll do for next week's 2 classes, Tuesday and Thursday, and the following week, Tuesday class, we'll do an extra 30 minutes. So we'll go from 5:30 to 6:30, and that way we'll make up the hour-and-a-half class we'll miss on Thursday.
They go from 5 to 7.
Huh?
5 to 7.
5 to 7. I'm sorry, 5 to 7. Where am I thinking? 5 to 7. Next week, Tuesday and Thursday, and the following Tuesday. And once we do that, we'll go back to 5 to 6:30.
Okay.
Is that all right? Okay. And it'll all be recorded. Yes.
We only just need to make up one day. You said Tuesday, Thursday, and the following Tuesday.
Okay, yeah, but you see, it's an hour-and-a-half class.
Oh, yeah.
Hour-and-a-half class. Yeah, so that's why I said,
Okay.
15-minute makeups or 3 30-minute makeups.
No, you're doing Tuesday, Thursday, Tuesday.
30 minutes each day, that's an hour-and-a-half, and that makes up for the hour-and-a-half we miss on Thursday. Is that okay?
Oh, okay, okay.
Can you do that?
Yes, sir. It is
All right.
on my head.
Okay. All right. So here we have the situation here. I'm not finished reading the problem yet. Now the worker pushes the cart. Okay. He pushes the cart with a constant force of 40 pounds. So his push on the cart, here's the constant force of 30 pounds. Or is it 40 pounds? 40 pounds. Okay. As shown in the figure. Okay. Now, how much work does the person do? What's the formula for work? What's the formula for work? Force times your displacement. Okay? I like to put a dot in there because it is a dot product. Okay? Now, I have 2 forces on the board here. Which one do we use? The weight, 350 pounds, or the pushing force, 40 pounds?
The weight.
The which?
The weight.
Okay? Here's one major reason why not. Because the force must be in the same direction of the displacement. You see, that force is in the horizontal direction, displacement's in the horizontal direction. If he was pushing it through the floor, yeah, then he would do that. But he's not. That's just the weight of the car on the floor, and that's being offset by the normal force of the floor on the cart. Okay? So those cancel out. Those are not a net force. This is a net force. Okay? That's a 40-pound force. Now, my arrows aren't to scale because I drew it too near the bottom, but it's only the force in the direction of the motion, not the weight of the cart. The wheels are supporting that. He's not having to lift the cart and carry it. If he was, then that would be included. But see, the wheels are supporting that. The floor is supporting that. He's not having to do anything with that. He's just pushing with the 40 pounds of force, a constant force. So this would be, say again?
That would be 350 times 30.
No, not the 350. the 350 is perpendicular to the force. That force is not creating the motion. That's just down on the floor. Floor is pushing up with that, with the normal force up here, and those cancel out. This is the force that is producing the motion. So it's 40 pounds, and that's got a bar over it. And I believe the displacement also had a bar over the 0. So times the displacement of 30 feet, okay? And that had a bar over it too. So what is the work done? 1,200 what units? Not pounds. No, not feet. Say again? Not per feet, foot pounds or pounds feet. It's multiplied. We usually say foot pounds. Okay? Foot pounds. Now, do I need any bars over either of those zeros? No, because two significant digits here, two significant digits there. There's our 1, 2 significant digits there. Those zeros are insignificant. They're important because it's 1,200, not 12 or not 120, but they're not significant digits. 1 and 2 are the only significant digits. Does that make sense? Okay. All right, let's see how the book did. Goodness gracious, they got it right. Good for them. All right. Now, the cart weight of 350 pounds was sort of just unnecessary information, not needed to solve the problem. So there's not anything such as conservation of data given. You just use the data that you need. You don't have to use every number in the problem. The work is done by the worker pushing the pallet, and the force that he pushes on the pallet, that's the force that you multiply by the displacement. Okay? And the definition is, I'll say it again, the product of the force in the direction of the motion, okay, times the magnitude of the displacement. All right. Now, this next little bit here gets into some trigonometry. And y'all haven't had trig, I take it, or have you? Okay? So what I'm going to do, in the past I've always taught this, and I'll just go over it quickly with you, but you're not going to be responsible for it. And I hope that the, in fact, let me take a look and see if I have a copy of the test here. I think I tried to avoid problems that had angles in it. I know in some later chapters I inadvertently included some. Okay. Yeah, the test will not include any trig problems on it. So what I'm going to do now is get out of here and go to the other slide, and this is the one that describes what we're doing. Now this is just for your viewing pleasure. You're not responsible for this, but this is what I was describing when I was pushing on the chair here. Don't worry about it, you don't have to know it. But this is a block. You got a rope tied to the block. You're pulling on the block. Okay? You're pulling with that force. The block's going to come in this direction as long as you overcome the static friction. Okay? Since the block's going to move this way, your force that way, do you multiply this force by the amount of displacement? No. You have to break this force into two components, a horizontal component and a vertical component. That's what you do with vectors. You break them into their components. It's only this component, the F sub x, that does any work on the block. This component here, they don't even show it, but it's F sub y. That does no work on the block because the block's not being lifted off the floor. It's sliding across the floor. Okay? Now, this is the angle theta in between the applied force and the horizontal, and that is how you determine that F sub x. We're not going to worry with it, but it's only that component. So when you pull a kid in a wagon, which you probably have done before, right? Okay? It's not the pull that you do here that is pulling the wagon. It's the horizontal component of that pull. Okay? So you break that into horizontal component and vertical component. Now, if you've ever pushed a kid in a wagon, you probably have realized that. If you're not wanting to stoop down very much and you're pushing this way, you have to push harder to get them to move. If you really get down and squat and push, you don't have to push as hard, but then it's hard to get down and squat, okay? The reason is pushing like this, part of your push is into the ground. That's not pushing the wagon. It's only the horizontal component that does any work, okay? So that's what this figure is about. We won't, let me just take a, yeah. We won't do any with it because that does require trig. And you haven't had trig, so I'm not going to do it. So we're going to skip example 3. Now example 4 is sort of a fun one to look at. I don't think they have this. Okay. There's a figure for example 3. We're not going to do that. Okay. Okay. And they don't do the figure for the next one. But it is sort of an interesting problem. It's Juan and Sonia are using a push mower to mow along. Juan, who is taller, pushes at a constant force of 33.1 newtons on the handle, but because he's taller, his angle is 55 degrees from the ground. Okay? Sonia, who is shorter, pushes at a constant force of only 23.2 newtons, so a little bit less, on the handle, but her handle is down there at 35 degrees. Okay? Now, who do you think is doing more work? They assume that each push the mower 3,000 meters. Okay? Who does more work and by how much? Just looking at the data, what would you guess? Who would do more work? Juan or Sonia? Sonia, why?
Because she's pulling 215 newtons. She's pulling.
No, well, she's pushing, but it's 23.2 newtons, but he's pushing with 33.1 newton. So on first glance, you would think he might be doing more work. But you see, his angle is greater, and because his angle is greater, part of that forces into the ground. It's not in the direction of the motion. So he's doing less in the direction of motion. She's shorter, so her angle is less, so more of her push is in the direction. Even though it's a lesser push, more of that is in the direction. As it turns out, they come out being almost exactly the same. We're not going to do the math because it requires the trig in it, and you haven't had trig. But if you look at the problem, you'll see they do almost identical amount of work. Okay, both rounding to 57,000 joules of work. But that's using cosines. Now, are y'all at all familiar with sines, cosines, and tangents? At all? Okay. Just so you know, there is a little saying. This is a right angle here. Between horizontal and vertical, that's a right angle. So that makes a right triangle. Here is your angle, 30 degrees. The sine of the angle is the opposite side over the hypotenuse. The cosine is the adjacent side over the hypotenuse. And the tangent, which we're not going to use in these problems, is opposite over adjacent. Now, you don't need to know this, but if you ever do need to know it, here's what I just said. Let me get my pen back. Okay. I can't get that, so I'll get this one. Okay, can't get it. There we go. Okay. The sine of theta is equal to opposite over hypotenuse. The cosine of theta is equal to the adjacent over hypotenuse, and the tangent of theta is equal to opposite over adjacent. Okay? Now, I always just memorized them that way, learned them that way, way back when I was in high school, wherever. But first time I taught trig, this was over on the Bessemer campus 20 years ago probably, a woman in the class used this. She said, "Some old hag caught another hag taking oats away." I'd never heard that in my life. Now, I had had a roommate who used this, and this to me wasn't very helpful, but saw ka toa, T-O-A. Same deal. But sa and ka sound so similar to each other, I had to know what they were meaning before it made any sense to me. Yeah.
We said Sokotoa.
Say again?
We said Sokotoa.
Sokotoa.
Yeah.
And I've heard people say that. That makes more sense. Sokotoa. Okay? So you have had some trig. Yeah. Then later, I had another gal in the class, and she said she learned it by some old hen caught another hen taking oats away. Well, I like hens better than hags, so I go with that one. But you don't need to know it. But Sokotoa makes more sense because you can see it, but you can tell the difference there better. Okay. So, just in case you ever need trig, those are the little, and you'll see the adjacent side is the one adjacent to the angle, the opposite side is the one opposite the angle, and the long side is always the hypotenuse, the side that's opposite the 90-degree angle. So those where you get it. So this is the component in the direction of motion, the adjacent side. That's why they use cosine. The opposite side is not doing not contributing to the work on the cart at all. Okay. So homework exercises here, because every one, example 5 also uses, or does it? No, it doesn't. We can do example 5. So let's do example 5. I think what I'll do is go back to my white sheet. All right, we can do example 5. Find the amount of work done in vertically lifting a steel beam with a mass of 750 grams. So here we're going, let me get my pen set up again. This is on page 206, okay? So here we're going to lift a steel beam. So we're going to have the big old beam here, okay? We're going to tie it here and here, and with a big old lift it up, okay? We're going to lift a steel beam, and the mass of this beam is equal to 750 kilograms. That's pretty heavy, okay? At a uniform speed, a distance of 45 meters. So you're going to lift from here to there, and this is going to be 45 meters, okay? Again, no bar over the 0, and just 45. What we're looking for is the work. Someone tell me what work is. What formula do we use for work? Force times displacement. And they use S for displacement. I like D, but S is fine. Okay, work is, and that's a capital W, by the way. Okay, work. Little w is sometimes used for weight, so don't confuse those two. Okay? Now, how are these things related? What in the world is our 45 here? Of those units there. That's going to be your displacement. It's a vertical displacement. Now, what's going to be the force?
750 kilograms.
Except that is a mass. It's not a force. You have to calculate the force in this problem. What force are you having to lift? Say again?
750 kilograms.
No, okay, that's mass. That's not force. What force are you having to lift? Again, force is what I get when I stand on the scales.
9.8.
Say again?
9.8.
Okay, that's involved with it. That's the force due to gravity. That's what you're having to work against. And that's going to be your weight. And that's going to be M times G. Remember that one? See, all these formulas, just because we did them a chapter ago, we're still going to be using them over and over again. So you have to first calculate the weight, which is your mass times your acceleration due to gravity. And the mass is 750 kilograms. And your acceleration due to gravity, as you said, was 9.8. What units?
Meters per second.
Meters per second squared. Perfect. It's an acceleration. So when you multiply that, you'll get something on the order of 7,460, something around there.
7350.
7,350. Is that right? Okay. So the work done is 7,350. Is that right? Yeah, okay. Yeah. That would be, what unit is that? Kilogram? Yeah, that's a Newton, okay? Times the displacement of 45 meters. Now, you might say, time out, wait. That's too many significant digits, isn't it? Well, I don't worry about in the middle of a problem having extra digits. It's only the answer I'm worried about. So I'm going to use all those digits. Every one that's on your calculator, 7,350 multiplied by 45, and what do you get as a result?
330,000.
A little louder.
330,750.
Okay, 750 what unit?
You okay?
Yes, fine. I just sneezed loud.
Newtons per.
It's Newton meters or joule. Okay, I'm pretending I have a ring, a joule on my ring. I don't. Okay, now this is your final answer, and this is the one we worry about significant digits. How many should we have? You're given only 2 here, 2 here, so your answer can only be 2. We use 2 for the acceleration due to gravity, so we will use round this to 3, 3, look to, I can't write, 3, 3, look to the right, that's a 0. We're not going to do anything with the 3, 330,000 joules. Okay, it doesn't seem fair to throw those away, but significant digits, that's what we do. And they actually write it as 3.3 times 10 to the 5th joules. That's another way to write it. 3.3 times 10 to the 5th joules. Now, do you understand scientific notation and how they got that? Okay, what you do, this is your answer. Here's your decimal, right? How many places do we move it? 1, 2, 3, 4, 5. That's why it's 3.3 times 10 to the 5th joules. Because you have 10 to the 5th is 10,000. Yeah. And so you multiply 3.3 by 10,000, you get 330,000. Okay, so that's, and in scientific notation, you only display the significant digits, 3.3. Okay. Does that make sense?
Do you
Now,
have to write it in scientific notation?
you don't have to, no. They just did, but I wanted you to be familiar. If you saw an answer in it and you had it in the other form, say, oh, that's the same thing. Now, here's another thing you could do. This 330,000 joules, that's a big number, isn't it? So if you're wanting to use a smaller number but a bigger unit, what would you do then? power of 3, how many, what is your metric prefix? Since this is a metric unit, joules, what's the metric prefix that stands for 1,000? Prefix, metric prefix. Okay, it's used on the street a lot. Kilo. Hey, y'all don't know anything about that. Okay, so kilograms means 1,000 grams. So if you wanted to use a bigger unit, you could use, instead of joule, kilojoules. Move the decimal 3 places, you got 330 kilojoules. The kilo K is lowercase, the J for joule because it's named after somebody is uppercase. That's actually, to me, is the easier answer. The scientific notation actually takes just about as much room to write as 330,000. But 330 kilojoules, that's really simple. Okay, so any of those answers are correct. Okay, homework exercises. You can do any of the odds, 1 through 5. And 3 and 5 don't have their numbers there, but they're the ones under 1. Okay. You can do 7, 9, 11. You don't need to do 13 because that has an angle in it. Okay. You don't need to do 15. Because that has an angle in it. Or 17. But you can do 19, 21, but not 23 because that has an angle in it. Okay? So those are the ones you need to do. Don't worry about those things. If you want to play with them, you can. Yeah, but it's not necessary.
Finding the coefficient of friction problem since
okay.
I wasn't here.
All right. Do you remember what section that was in?
It was the last section, the last class. So 5.4 maybe?
Oh, back in chapter 5. That's right. Okay. Let me go back to chapter 5. Okay. You find one. That you would like me to do. Oh, yeah, you don't have a book. I'm sorry. Okay. Number 1 has a coefficient given. So does number 3. Number 5 is asking for the coefficient of friction. So which one do you want? Number 7 has a coefficient given. Number 9 has a coefficient given. Number 11 has a coefficient given.
We do 7.
Number 7? Okay. So let's clear this screen. Any questions on this before I clear it? Okay. All right. So we're going back to page 134. Okay. This is problem set 5.4. And number 7. All right. A tow truck can deliver 2,500 pounds of pulling force. So here's the tow truck. I'll just call it a big old truck here, you know, whatever. It's pulling 2,000. I'm going to put pulling force of 2,500 pounds. And notice they didn't put a bar over it, so that's only 2 significant digits. What is the maximum weight the truck can the maximum weight truck that can be pulled by the tow truck if the coefficient of rolling friction of the truck is 0.10. So here's this big old truck here pulling on the other. That's a pretty ugly truck. It's pulling on another truck, so let's put the thing down here. And here's another truck that it's pulling, okay? And this is rolling friction here. So this one is pulling in that direction. And what is the maximum weight truck that can be pulled by the tow truck if the coefficient of rolling friction is 0.1? So here we have our frictional force. Always resist the motion. So this frictional force, F sub F, okay, that is mu times the normal force. Okay, well, what's the normal force? Now, we're going to make an assumption here. We're assuming this is a flat, level road. Okay? Now, the weight of the truck, that's what we're looking for. That's F sub W. That's what we're looking for, the maximum weight of this truck. Whatever that weight is, that's going to be equal to the normal force. Because if the gravity's pulling the truck down against the road with F sub W, that means the road is pushing up, unless it's sinking into the quicksand, which we hope it's not, the road is pushing up with the equal and opposite, because it's not sinking and it's not flying off the road. So it must be in equilibrium. The F sub N is the same. So we could have written this as mu times F sub W. We usually don't, but we could have, okay? So this is the frictional force in this direction. It must be equal to the force of the tow if you're going to be pulling the truck. So this would be equal to mu times the weight of the truck, F sub W. And that's what we're looking for. And we know the mu is 0.10. Two significant digits. They told us that. So what is your weight of the maximum weight of the truck you could pull? F sub W, I'm going to put max, okay, is equal to divide both sides by 0.10. Okay, so this will be 2,500 pounds divided by 0.10. And that's a dimensionless quantity. Now you can do that with your calculator, or you can do it just by, here's what I like to do. Just move this decimal one place over, so it's dividing by 1. You have to move the numerator one place over. So that would be 25,000 pound truck. So even though the tow truck is going to pull with a maximum pull of 2,500 pounds, it can pull a truck if the rolling friction there is 0.1 up to 25,000 pounds heavy, because the ground supporting most of that is the friction is only 0.1 times that normal force. Does that make sense?
Is mu always equal to 0.10?
No, it varies.
They don't give it?
Yeah, they'll either give it to you or you look it up in a table. The table on page 133 may be the one, and that only gives a few. And you have to decide whether it's static friction, kinetic friction, or whatever. These are your mu's. They don't give a rolling friction there, but it's a, they gave that in the problem, so the truck is rolling. Now, if that truck being towed had flat tires and you're having to drag it, that friction coefficient is going to go up significantly, so then you wouldn't be able to pull as heavy a truck if you're having to drag those tires. Or if the brakes are locked or something like that, then that would change your picture altogether, but that makes sense, okay? Because the tow truck, if it's able to roll, I'm surrounded by cords, so I don't want to pull. Oh, I'll do this one, okay? If I were pulling on this, that's not too hard to do, or even better this, okay? That's not too hard to do because it's rolling. But if that was sitting flat on the ground, then if I pulled, it's going to be more like pulling on this. And that's hard to do. Okay. So rolling friction is usually much less than the others. Does that answer your question?
Yeah.
Okay. Any other questions? All right. Now we go to the next topic, and that's power. Okay? I'm going to get out of this for just a moment and see where we are on the other slide set. Oh, that's pages away. Pages away. Yeah, many pages away. Okay. So, we'll go back to my white page. Okay, we'll go from current slide. All right. Now, a little bit of refresher. Reminder. One of the first things we talked about was displacement, right? You were here, you moved to there. Okay, that's measured usually in feet, U.S. customary, meters if you're talking about SI units, but it could be other things, inches, miles, kilometers, furlongs, whatever, okay? That was a displacement. And then one of the next things we did was divide that by time. The time rate of change of displacement, that was your velocity. Time rate of change of distance was speed. Well, once we had that velocity, we could take the time rate of change of velocity and get acceleration. Okay? Divide the velocity by time, and you get a velocity will be meters per second. Distance divided by time, meters per second. Divide it again by it, and you get meters per second squared. That's an acceleration. See, our units are our friends here. Okay, now, we didn't talk about it. We skipped the chapter that dealt with momentum. So that was what I think Isaac Newton talked about a lot. He didn't call it momentum. He called it quantity of motion, which is mass times velocity. And you don't need to know that. But then you did a time rate of change of that, and that's where you got a force. Now, we call it mass times acceleration, but that's exactly the same as the time rate of change of mass times velocity. So time rate of change is something we do all the time. We have something, we see, so, well, what happens if we divide by time? What will that give us? Well, that's what we're going to be doing now, is we've been talking about energy or work, okay? We haven't said energy yet, but we will. And we're going to take the time rate of change of doing work. Anyone know what that is? The rate at which you do work. Time rate that you do work. That is what we call, let me get my pen back. That is what we call power. It's work divided by time. Okay? Power is work divided by time. And since work is a scalar quantity, time is a scalar quantity, power is a scalar quantity. Okay? Now, what are the units for it? In the SI units, what's the unit for work? Joule, okay. And time? Tick, 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 tick. Second. And a joule per second. What do you reckon that is? We haven't had it before, so you can make a guess. It's a watt. What? 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 Yeah, it's a watt.
A watt.
Watt. W-A-T-T.
Oh, a watt.
A watt, yes, okay.
Oh, okay.
Okay. Named after, I think his name was James Watt. He was a Scottish engineer who did a lot of the early work with power. Okay? So that's your unit for power. Now, don't confuse. Capital W as a parameter is work. Capital W as a unit, which will always have a number in front of it, that's a watt. Watt is a measure of power. Joule is a measure of work. So don't get those crossed up. Okay? Now, in the U.S. customary system, okay, what is the unit for work? Doesn't have a special name. Foot pounds, okay? And you still use second, so that's what we use there, foot pounds per second. But if you have a whole lot of those, like 550 of them, then we call that a horsepower. So 550 foot-pounds per second is 1 horsepower. That's not Hewlett-Packard, that's horsepower. Okay? Now, that came from, and James Watt, the guy that the SI system is named after, he's the one that came up with that measure. He said, what's the average work that a dray horse, one of those big old Clydesdales or something like that, could do in a day? Averaged over a day, that was 1 horsepower. And when you broke it down into a second, that was 550 foot-pounds of work every second. Okay?
What page are you on?
I'm sort of all over the place. Basically, page 208. Yeah, all that is on 208. So 550 foot-pounds per second is the same as 1 horsepower. That would be 33,000 foot-pounds per minute. Okay? Because you got to multiply by 60. Okay. Now, just a few conversions they have there. If you're trying to have a whole bunch of watts, like 1,000 watts, what would that be? To do a smaller number and a bigger unit, 1, what is a prefix that means 1,000? You just were about to say it. Kilo. Kilowatts.
Watts.
That means 1,000 watts. Okay? Now, if you had 1,000 kilowatts, that's called a 1 megawatt. Now, once you get the big units, 1 million or higher, you start capitalizing the prefix too. Kilo, K means kilo. That means 1,000 watts. So this would be 1 million watts. Yeah. So once you get past 10 to the 6, your prefixes actually get capitalized. That's a megawatt. And you'll hear them talk about a turbo generator or something like so many megawatts of power. You also hear them talk about bombs, atomic bombs or big bombs, and how many megawatts of energy are involved with that. Those are big, okay, megawatts, 1 million watts. Now, they have a little blurb there on human horsepower, which sort of sounds contradictory, but that's, you know what they're meaning. And you can read that if you'd like. It's fairly interesting. All right, with all that in mind, let's go to do example 1. And example 1, I'll do it on a clean page because we have take out most of this page. So let's do example 1. A freight elevator with operator weighs 5,000 newtons. So this is a weight, so it's called F sub W is equal to 5,000 newtons. This is on page 209, example 1. Okay. You sure you don't need a light on? Are you able to see that? Okay. Okay.
I've been flipping pages doing notes over here.
Okay. All right.
I'm with you now.
Now, if it is raised to a height, this is a freight elevator, so it's going up and down the shaft, and the weight of that with the operator and the elevator is 5,000 newtons. Okay, if it is raised 15 meters in 10 seconds. So here's the shaft of the elevator. It starts off down here on this floor and goes up 15 meters. And I don't think they have, yeah, they do have 15.0 meters. That's your displacement, right? S. This is your force, or your weight. Okay? Now 15 meters, this room is about 3 meters tall. I'm about 2 meters and another ½ meter. You could take my torso and put on top of me, and that just about do that. So that's about 3 meters. So 15 meters would be up 5 stories. So this is sort of what we're dealing with. This freight elevator is going up 5 stories or 15 meters. Okay? If it's raised to the right, and it's raised in 10.0 seconds. Okay? How much power is developed? Now, I think before we do that problem, let me step back and give another dumb example of power. Okay? Remember the story of me digging out the patio in the backyard? Remember that story? When I hit the rock and then grunted and pushed and shoved, but couldn't move the rock and was doing no work for a day or so, even though I was sweating and like crazy. No work unless I moved the rock. Okay? Well, that same story, let's go back to it. I worked for about 5 weeks digging on the patio. Finally got that big old rock to budge, but I kept digging and moving and stuff like this. And at the end of that 5 weeks, I basically had only about half of the patio dug out. Now, part of that is because that big rock took several days to get that dug out. But it came time for fall term to begin. Now I was just going to be working weekends. I didn't have the summer off like I did before. And I had half the patio still to dig. So that's going to take months and months and months. My wife didn't want to wait. Now the reason I was digging in the first place, there wasn't room between the house, the trees, and everything else to get a, what do they call them? Oh boy. Those machines that move soil for you, dig and that kind of stuff. What do they call that? It's a, all I can think of now is a bush hog. That's a mower. It has a name like that though. Whatever. Think of a ditch witch. It's a name like that, but it's not the same. Okay. Anyway, I may think of it later. We couldn't get one in there because we didn't have enough room. But by the time I got half the patio dug out, there was plenty of room. Bobcat, that's what it is, to get a bobcat in there. Okay? So here we were the last weekend, this Labor Day weekend before classes were going to start back. We were on the quarter system back then, so that's when they started the first Monday after Labor Day. So this was or maybe the Tuesday after Labor Day. So we needed to get the rest of the thing dug out. So we called around, found a guy who operated a bobcat. He gave us a decent price, so he came over to dig out the rest of the patio. Okay? And in 1/2 of a day, he moved as much soil as I had moved in 5 weeks. Now, what was the difference in that picture? The work done was the same. Same amount of soil, same weight of soil, same. Now, actually, I did more work because I actually moved it down and built it behind the retaining wall. So I was actually doing a little more work. But we're not going to count that. Just digging the soil out. 5 weeks it took me to dig out soil. In half a day, he moved the same amount of soil. Didn't move it as far, but he moved it. What's the difference in that picture? The work done was the same. What was the difference? Time. And what is time? What does time involve? Power. You increase the time, you decrease the power. Decrease the time, increase the power. And I'll promise you, that big old bobcat that he brought in there, I'm guessing was at least 250 horsepower. And I'll tell you this, I'm considerably less than half a horsepower. So that's why it had so much more power than I did, so it could do the same amount of work in a very small fraction of the time. Okay? That's what power is. Work per unit time. So the Bobcat had much more power. He could take much less time. Okay? So that's why time is involved. This is your time here. Okay? So what is the power developed? Now remind me again what the formula for power is. Work divided by time. But what is work?
75,000.
How did you get that? It's absolutely right.
I multiplied and then I divided. I multiplied 5,000 newtons and then
Yes.
I multiplied 5,000 newtons times 15.0. It gave me 75,000. Then I divided
By 10.
5,000.
Perfect. Work is force times the displacement, as long as they're in the same direction. Where your force is up because you're overcoming gravity, your displacement is up. Okay, so they're in the same direction. So that's force times displacement divided by your time interval. And you're absolutely right. That was 5,000 newtons times 15.0 meters divided by 10.0 seconds. Okay? Now you can do it any way you want to. You did it absolutely correct. I'm going to be a little lazier than you. I'm going to wipe out a 0 first. Okay? And then it'll be 500 times 15 times 15 would be 7500, right? And that would be what unit? Say again? No, Newton is here. No, kilograms is mass. We don't even enter that here. Okay. You could say kilogram meter per second. That certainly would be right. I mean Newton meter per second. Newton meter per second. But what is a Newton meter? Oh, we know what a Newton meter is. Joule. So that would be a joule per second. But what's a joule per second? What is a joule per second? What?
A watt.
Watt. Okay. A watt. Watt. Yeah, okay, that's a watt. So our 7,500 watts. Or if you wanted a smaller number but a bigger unit, that would be
Kilowatts.
how many?
7.5.
0.5, actually 7.50. Because if you'll notice, 3 significants there, 3 there, 3 there, so I should have a bar there and there, or 7.50 kilowatts. Okay? Is this feeling a little more comfortable now, or is it still sort of mystery meat?
You know, after I got down to that part, to the 7,500, you know, I looked over here at the 5,000 newtons. I didn't have anything to take the newton out. I didn't have anything to take milligrams per second out. So that's why I put it down here.
Okay? Well, they're not going out. They're multiplying together. This is a Newton meter, and a Newton meter is a joule.
Right. But
And a joule per second is a watt.
Okay, do I have to put joule?
You don't have to. You can put any one of those units. Newton meter, joule, or watt. Okay, it's Newton meter per second, a joule per second, or a watt. All those mean the same thing.
So let me ask you right there where you, right up at the top where you had, yes, that. So do I have to come, can I leave it like that, or do I have to come down and put 75?
No, this is a perfectly good answer.
Okay.
Yeah.
Because it get confusing all over the place.
Yeah. But if your answers in the back of the book says watts, then you say, oh, but that's a joule per second, and that is a watt. Yeah, that's the same answer. Yeah, exactly. So the main reason to let you is so you're conversant with all the different ones. Now let's see what how they put their answer. They left it as, well, no, they didn't. They wrote the answer as 7,500 Newton meter per second, but then no, and they just left it right like that. So yeah, that's perfectly fine. Nothing wrong with it. But if, you see, I'm lazy. I don't like to write in M per second. That's just too much writing. So I said joule per second, but that's still too much writing. So I'll just put a watt. That's much less writing. I'm lazy, okay? You don't have to be lazy. You can be a hard worker, and it works too. Okay? Now, all right to erase that one?
Yes.
Okay. Let's do example 2. The power expended in lifting an 825-pound girder, that's like a beam again, 825-pound girder, here's this beam again, okay. Okay, going to lift this thing, that's a weight, F sub W is equal to 825 pounds. Okay? The power expended in lifting that girder to the top of a building, ooh, wish I hadn't drawn it so big. This building is 100 meters high. So that girder is way too tall. I mean, way too big here. Okay, no, I'm sorry, 100 feet high. Okay, that's not quite as bad, but still pretty tall. Now, like I was saying, I was estimating this room is about 3 meters tall. If you use that same estimate, that would be about, let's just say 30 feet tall. No, that's not right. About 10 feet tall. Is that right? Yeah, that would be better. 30 meters, yeah, it would be about 10 feet. So let's just say this is a 10-foot high room. So 100 feet would be a 10-story building, okay? So this is about a 10-story building. We're going to lift this thing to the top of the building, somewhere up there, 100 feet high. And you're going to use the power expended as 10 horsepower. So your power here is 10.0 horsepower. Okay? How much time is required to raise the girder? So now we're seeing what is the time. Okay? Now, on first glance, is there any problem with this problem? Say that again.
You're doing the pounds and the...
Okay, you're hitting right on it. Here you have pounds, feet, time will be in seconds probably. Horsepower, how does that figure into it? You need to get that into how many foot-pounds per second. So how many what is a horsepower?
550.
Okay, that would be 10 times 550. This is horsepower, and this is foot-pounds per second per horsepower. Okay, that's what a horsepower is. So that gets it into that. So when you multiply that out, the power expended is 5,500 horsepower. I mean foot-pounds per second. Foot-pounds per second. 10 horsepower times 550 foot-pounds per second per horsepower, that would be 5,500. Now, you have the bar over that one, because 3 significant digits there, 3 significant digits there, 3 significant digits there. Yeah, I didn't put that one over it, but it had one.
Bar just means to stop at that digit for significant digit?
Yeah, that's where you stop. You go 3 digits from the left, and that gives you the significant digits. Okay. Now we can set up our problem to go. How do we do this? What is power?
Work divided by time.
Work divided by time. Okay, time is what we're looking for. So let's swap that around and solve for time. What would that be? Time would be
Work times power.
work divided by power. Do you see that? You just flip those two. Pretend you had your triangle or your circle, draw them in, and this would be work is on top, So time is work divided by power. Okay, but what is power? Oh, well, okay. So your work here, you have to figure the work. And what is work? Okay, it's your force times your displacement divided by power. Okay, your force here is your 825 pounds times your 100 feet. Okay, well that's not a minus sign, that's a times, divided by 5,500 foot-pounds per second. Okay, now that's ugly writing, but hopefully you can follow it. So it's 825 pounds times 100 feet, that would be 82500 foot-pounds divided by 5500 foot-pounds per second. And, okay, now you see what happens here? Units are your friends. The pounds cancel out, the feet cancel out, and the 1 over second flips up and becomes seconds. So how many seconds did you say? 15, probably 0.0 seconds, right? You need 3 digits, so you put a 0.0 after it. Let's see how the book did. 15.0 seconds, good for them, okay? Now in that we used a conversion factor. We knew that power and horsepower is 550 foot-pounds per second. We had 10 horsepower, so it's 10 times 550, giving you 5,500 foot-pounds per second. Then we could use it in the formula here because you have foot-pounds in the numerator, foot-pounds per second in the denominator. Yeah, you can get seconds as an answer. Does that make sense? Please say yes, okay?
Yeah.
All right, good deal. Need it up here a little longer? Okay. Let's see if we can squeeze in example 3, is it? Okay. So let me clear my screen here. And let's do example 3. The mass of a large steel wrecking ball is 2,000 kilograms. Okay. So here's this big old wrecking ball. Okay. And the mass of this ball is 2,000 kilograms. That's a mass, by the way. What power is used? So we're looking for power. That's the unknown here. Okay. What power is used to raise it to a height of 40 meters? So it was down here on the ground, and you're wanting to raise it up here to 40.0 meters. So you're having to lift that ball, and we're wanting to know how much power it's going to take to lift it 40 meters. If the work done is in 20 seconds. So this is going to be your meters measures your displacement, which is S, and the work done in 20 seconds. So that's going to be a measure of your time. Okay? And we're looking for power. Okay? And what is power? Work divided by time. We got the time, but we don't have work. What do you reckon the work is?
That's time power.
Okay, you could go that way, but that's, we want to know fundamentally what's work.
You gotta multiply first.
Okay, multiply what first?
You gotta multiply 2,000 kilograms times 9.8.
Okay, very good. Work is force times the displacement. That's what work is, right? Okay, divided by time. Well, we got displacement, we got time, but we still don't have a force. And that's it, what you were saying. A force is, or weight, this is your force due to weight, this is your mass times your acceleration due to gravity. times your displacement, that divided by time, that is going to give your power. So yeah, string it out here and see what you got. Your mass of 2,000 kilograms times, what is your G? G, what's your G? What value? It's the measure of G, acceleration due to gravity. 9.80 we'll use because that is that. And what units? Meters per second squared times your displacement. That was your 40 meters. Okay, and divide all that by your 20 seconds. Okay, now I'm going to be real lazy about this, and I'm going to divide 20 into 40, and that'll go 2 times. Okay, so 2 times 2,000 is going to be 4,000, and multiply that by 9.8, and that's going to be 39,000 or something like that. Someone do it. 39,200, and that would be a kilogram meter squared per second squared per second. Kilogram meter squared per second squared is a joule divided by second. That will be a what?
A watt.
A watt. Very good. Okay. Now, you need 3 significant digits. We got it. If you wanted a smaller number but a bigger unit, that would be what? 39.2 kilowatts. Excellent, excellent, excellent. Let's see how they did it. 39.2 kilowatts, or 39,200 watts. Very good. All right. Do we have time for one more? What say ye? Yes. Any questions on this one? Okay. Then let's clear the screen. And let's try example 4. A machine is designed to perform a given amount of work in a given amount of time. That means it has a certain power rating. A second machine does the same amount of work in half the time. Find the power of the second machine compared to the first. Oh, this is one with no numbers. So let's say machine 1, okay, designed to perform a given amount of work. Let's call that work 1 in a given amount of time divided by time 1. Okay, so this is going to be power 1 for machine 1. Okay. Second machine, machine 2. Okay, we wanted to figure out what power 2 is compared to power 1. Okay, it's going to do the same amount of work. So if it's the same amount of work, we can call it W1 again. Okay, same amount of work. But it's going to be half the time. So that's going to be 1/2 of T1. Right? Got it? Now, what we can do, since we're dividing by 1/2, you can multiply numerator and denominator by 2, and that will wipe out the 1/2 in the denominator, and that gives you 2 W1 over T1, which is twice your first power. So if you've got a machine that can do the same amount of work in half the time, it has twice the power. So if that first machine was, say, 5 horsepower, just making something up, motor, the other one's going to have to be 10. Because if it can do the same work in half the time, it has to have twice the power. Does that make sense? Okay. Wow. That was a little bit easier than I thought it would be. Thus, the power is doubled when the time is halved because it's an inverse relationship. Okay, now I'm guessing we may not have time for number example 5. What say you? Think we can squeeze it in or not? You tell me what you want. Once upon a time, I had a pencil out here, and now I seem to have lost it. Now, I know I had it here.
It's on the floor.
On the floor? Okay.
No, it's by the wheelchair.
It's what?
By the wheelchair.
Oh, I see it. Okay. Thank you. This gal over here stole it from me. I'm sorry. Okay. She liked that it was wooden. Okay. Are we going to have time to do example 5?
Yeah.
Huh?
Yeah.
Yeah. All right. Let's go for it. Okay. Can I change screen?
Yep.
Okay. Example 5. A motor is capable of developing 10.0 kilowatts of power. So that's your power, right? How large a mass, so we're looking for mass. This is the unknown here. How large a mass can it lift? 75 meters. What's that a measure of?
Displacement.
That's your displacement, S. Oh, I've got to sneeze, sorry. Y'all awake yet? Okay. 75 meters is your displacement in 20 seconds. So 20 seconds is a measure of your time. Okay. Now, what formula is going to relate all those things together, or at least some of them? Okay, that's your unit. What formula? What one have we been using this whole section? Power is equal to, okay, okay, wait. Work divided by time. And what is work? Force times the displacement over time. So we got our displacement and time, but we still don't have our force. How does it relate to mass? We got our S, we got our time, need the force. How is, and this is force due to weight. What is that going to be? What is your weight? Oh, we had that one back in the last chapter. We've used it already tonight. The force due to weight is, a force is always a mass times an acceleration. What acceleration are we talking about here? No, acceleration. Acceleration due to gravity. You're lifting this thing against gravity. So it's mg, that's your force, times s, times divided by t. Now you got them all accounted for, except we just have to figure out what g is. Okay, we know everything except the mass. So you want to resolve this for mass, or you want to plug in and then solve it. You can do it either way. Let me show you how to do it this way. If you're trying to get mass, that's what we're looking for. That's the unknown here. Let's multiply both sides by time. That will get it out of your denominator. Okay? So now you have P times time is equal to mg s. You're looking for the mass. So let's divide by gs. Divide by gs. Okay? The g's go out, the s's go out. Now you got mass is equal to power times time divided by acceleration due to gravity times your displacement. Now you just plug and chug. Okay? Power is 10.0. Now it says kilowatts. Well, a kilowatt is a kilojoule per second. Remember, a watt is a joule per second. So this is a kilojoule per second. Okay? Times time, which is your 20 seconds, 20.0 seconds. We're going to divide that by your G, which is 9.80 meters per second squared, and also by your displacement of 75.0 meters. Yeah, we'll do it in just a second. Okay. Well, what is a kilojoule? One thing we can do, we can wipe out the seconds here, so that would be good, I think. Well, a kilojoule is a joule is a force times the displacement. So this is a kilonewton times a meter. Okay. Well, now the meters can go out. Okay. Well, what's a newton? It's a force is a mass times an acceleration. So that kilonewton would be 1,000 kilograms, okay, times meters per second squared. Okay, the meters per second squared go out, and that leaves you with kilograms, okay, or actually thousands of kilograms. So what we're going to do is multiply these things out, see what you get. The numerator is pretty easy. 10 times 20 is 2,000. Divided by 9.8, and then divide again by 75. I think what I want to do is let's just go on and put, instead of kilojoules, put 1,000 joules. Okay? 1,000 joules, because kilo means 1,000. So now we've got, it's 2,000 times 1,000, that would be 2 million, divided by 9.8 and divide again by 75. And see what you get. $2 million divided by 9.8 and divide again by 75.
2,721.
Okay, 2,700 and what? 21 kilograms. So that's the mass. That's too many digits, significant digits. We have 3 here, so that'd be 2,000. Count 3. 1, 2, 3. The next one's a 1. Replace it by 0. 2,720 kilograms. Okay. Whoa! They don't get that. Did they forget? Oh, no. No. They've still got to divide. Yeah. I think we left out something somewhere. Let's go back and see what we had. 10 kilojoules, that was right, wasn't it? Times 20, that's 200, not 2,000. Sorry, 200. 200, not 2,000. Okay, and that will give us, yeah, I'm sorry. I was doing it in my head and doing too fast. Whoops, I hit the wrong key. All right. Yeah, divide, yeah, that's 200 times 1,000 is 200,000 divided by 9.8 and divided by 75.
Still give you 0.2721.
Okay, wait.
27.
Okay.
2.72.
You know what? They round, well.
Yeah,
they
okay.
didn't round it off.
Yeah, they dropped the 1. Okay. So this is 200 times 1,000. That's 200,000 divided by 9.8 divided by 75.
Okay.
And see what you get. I think you'll get 272 on the note. I mean, you'll get 272.1.
That's what I got.
They dropped the 1. Yes, very good. So that's how many kilograms. All right. Now I think we have gone over, haven't we? But guess what? There's no extra charge. Okay? And starting next week, I won't be here Thursday. Starting next week, we'll go till 7 on Tuesday and Thursday, and then following Tuesday, and then after that, we'll go back to 6:30. Is that going to be okay? All right. Good deal. And we'll pick up next time with example 6. Let me give you a few homework exercises in 213. Huh?
In 213, okay, we got to put it up.
Yeah. In 213, you can do either 1 or 3 or both. And then you can do some of the odds 5 through, let's say 5 through 19. That probably will be pretty good. Okay? And then we will pick up from example 6 and move on. All right. Good deal. Any questions? All right. If there are no questions, I'll go on and shut it down. Is that okay?
Yep.
Okay.